So we are doing the following exercise, namely you have a partition function and we want to apply the renormalization group to this, and the way we are doing it is to split this sigma. So we put a label q here and we split this sigma q to sigma 0 q, where these q's have high momentum greater than half. So here q is greater than half and here q is less than half. So we split it into low momentum and high momentum modes and integrate out the high momentum modes. So we write this as d sigma naught q and do this integral. Okay. After you've done this integral, you get a effective action with some h prime where this has to be evaluated from that. Just do the integral. And as I said, the procedure for doing the integral, you can do whatever method you like. The simplest method is to use Feynman diagrams in perturbation theory, and we did work a few out. And now here, now you have, this is actually the final answer, but what you want to do is to do some rescaling to write this thing. So you do some rescaling. So I'll remove the 0 here. And the point of the rescaling is now this new variable q prime is 2 times the old variable. So the range of q prime is again from 0 to 1. And you've chosen the normalization of sigma prime so that the kinetic term, remember this had a kinetic term which was q squared plus r plus interactions. The interaction was a quartic. So we choose the normalization so that this thing continues to be q squared, half q squared plus something else. So this will become here an r prime. So this will have a normalization q squared, q prime squared plus r prime plus more. Okay. And this more, what is a, here there's a u, here there will be a u prime, u times quartic, sigma, 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 sigma. Here there will be a u prime, sigma, sigma, sigma. Okay. So what is the end of this? We get back our partition function in exactly the same form that we started with, except with a different r prime and a u prime instead of r and u. And then the idea is to repeat the step. So that means you divide this sigma prime again into sigma naught and sigma 1 and integrate out and keep iterating it. And what we did last time was to evaluate r prime and u prime in some approximation, u and r, and basically there were two diagrams that are involved. This is the interaction vertex. There's one diagram like this where this will be sigma naught, sigma naught. This will be the sigma 1 propagator because that's what you're integrating out. And we had another diagram like this. So this diagram is just a simple loop integral. This is also a simple loop integral. And at the end of the day, you get a quadratic term in sigma naught, which contributes to this thing. And this gives you a quartic in sigma naught, which contributes to that thing. Okay. And we did the diagrams in some approximation, very crude approximation. So you had some diagrams like dq or ddq 1 by q squared plus r, where half is less than q is less than 1. And we just did an approximation. We said since q is a number ranging from half to 1, let's just approximate it by some constant by 1 plus r times d dq. And for the purposes of our discussion, this is not important. All we really, the precise details of this integral are not important. All we need to know is that it's some function linear in R in the denominator times some number. So we did this approximation and we got the final result, which I'll just write down now. So we got a recursion relation. RL, 4 times RL is 3C UL by 1 plus RL. And UL plus 1 is 2 to the power of 4 minus D times UL minus 9C UL squared. Okay. So remember this normalization, this factor 4 was there in the Gaussian case also, just 4 times. It comes from dimensional reasons. And here also you can show that it's just dimensional reasons because we're doing it in a dimension D. The effective dimension of this you can show is 4 minus D, but the way we got it was we chose the normalization to get this kinetic term in this form with a half, with this half. And when you put in that normalization into the quartic, you get a relation like this. Why do we make it? Why? No, you want to evaluate this integral ideally exactly, but what we are saying is let's do it approximately. It's a finite integral with q in the finite range, and we are only really interested in the r dependence. And roughly speaking, it's going to be something with an r in the denominator. This coefficient may not be exactly 1, but you can always write it as some number by a plus b r, right? It's going to be something like that. So we just wrote it like that. Those details will not be important for the discussion. So it's a very crude approximation. You can do it more exactly. The qualitative details are not going to change. And this integral also we approximated it using the same thing. So that's why there was we took out the 1 plus r and we got a 1 plus r squared because there's a 1 plus r from here and a 1 plus r from there. We just took it all out, got 1 plus r squared. Okay. So this is our, if your starting Hamiltonian had these parameters, your new Hamiltonian will have these parameters. And I also pointed out that there will be other diagrams which will generate higher diagrams, sigma naught, things like that, which are there, but we won't worry about them because they're not. They won't affect the behavior that we're talking about. So these are, for the moment, we neglect them. In an exact calculation, you cannot neglect them, but for this approximate calculation, you can. Okay. Okay. And of course, each time you do the recursion, your C becomes L plus 1 becomes half of CL. Okay. Keeps going, becoming half. This reason, as I said, is just because you have changed your units. Unit of length has doubled, so your correlation length, which is a physical quantity, doesn't change, it just becomes half. So this is where we are. And then we said, let's look for fixed points. So generically, you'll keep flowing. So the simplest behavior you can imagine is that it goes to some fixed point and then stops flowing. So we try to find if there are fixed points to this equation. Namely, you want UL plus 1 to equal UL and RL plus 1 equals RL. And we call that number U star and R star. So let's see if there are solutions to this. And we found a solution. So one solution, of course, is R star equals U star equals 0. Trivially, that satisfies this, right? If you put U and R equals 0, it's trivially 0. So this is always satisfied. This was the fixed point we had anyway when U was not 0. When U was 0, so this is called the Gaussian fixed point. but we want something non-trivial. This is a trivial fixed point. We want something non-trivial, so we'll try to get a non-trivial solution. And the key was to keep this parameter as a small number, epsilon, and do perturbation to lowest order in epsilon. Can you find a solution where u and r are non-zero? And I should point out that if this whole scheme is to be trusted, you have to have u small, because this is valid. This is a perturbation expansion. So if you find a fixed point where u has a large value, that's not reliable. You can't use this. So you have to find a fixed point where u is small. And the trick that Wilson employed was to use this as a parameter and do the calculation in 4 minus d direction. Now the first thing you can see is if d is greater than 4, so of course we are interested in a fixed point for u equals 0 is always there. We want a non-trivial fixed point. But if d is greater than 4, you can see that ul plus 1 is going to be smaller than ul each time. Okay? This is if d is greater than 4, this is less than 1. So ul plus 1 will be smaller. So each time it will go and it will end up in 0. So you won't find a fixed point if d is greater than 4. If you want a fixed point, you have to have d less than 4. I mean fixed point meaning non-zero value of u. Then you have to have d less than 4. So fixed point will be 0. So try d less than 4. And then we solved it. So I won't go through the algebra. We found a solution where u star is basically, and we made some approximations. It's 2 to the power of 4 minus d minus 1 by 9c, and r star is minus 4c u star, where we assumed that r is small, assuming so where did we use this assumption? We dropped some of the r's in the denominator. So there's an 1 plus r, so if r is much less than 1, you can drop that r, and in that approximation we are able to solve it. So this is a fixed point. So this is basically epsilon, so this thing is epsilon log 2 by 9c, and this one, so if you put this value of u star here, this is minus 4 by 9 epsilon log 2. So this is u star, this is r star. So this is the what is it called, the Wilson-Fisher fixed point. So you can see the importance of epsilon being small. Okay, it's multiplied by, so if epsilon is small, u star is small, and r star is small. And when epsilon is 0, of course they're both 0, and you get the trivial fixed point. Okay. So now we have two fixed points, and so let's see how the system actually flows when you're a little bit away from the fixed point. Okay, so here's your curve u. So I'll write, what is this, u n plus 1 u n. So if you look at this recursion relation for u, r of course keeps growing. Okay, so unless you're very close to 0, this will just keep growing. So as you can see, r is very close to 0. Let's look at this. When epsilon is positive, un plus 1 is greater than un. Okay, so if this is the curve, let's say this is a 45-degree line. So this is the curve where un plus 1 equals un. It starts off positive, I mean greater than this, and then because of the minus 9 u squared, it goes like that, decreases. Okay, so this is your fixed point u, because this along this line ul plus 1 is the same as un, or un plus 1 is the same as un. So this is the actual curve, and at this point it meets the 45-degree line. That means un plus 1 is the same as un. Okay. But now graphically you can just analyze what happens if you're a little above or a little below the fixed point. So imagine you're over here. So imagine you start, so this is your fixed point. So imagine you start there. Then this is your un. Then the value of your un plus 1 is this. Okay. This is the value of un plus 1, which is less than, so this is if at this point un plus 1 equals un. So here un plus 1 is less than un. So your next point is over here. And then you go again. Again your un plus 2 is again less than un. So your next point is here. And you keep going like that. So if you want, you can put an arrow like this. You keep going like that till you hit this point. So it's going towards the fixed point. And you can check if you start from here, the same argument. You start with your un here. Then un plus 1 is here. And un plus 1 is greater than un. So the next iteration you're starting over here. And then you go up there. Sorry. So again your un plus 1 is greater than your un. So you keep approaching this side until you hit the fixed point. So either side, you start from either side of the fixed point, you go towards the fixed point. Okay? So that's a nice feature of this fixed point. If wherever you start, you end up near that fixed point. So what does that mean? As you go, each of these iterations is going towards lower and lower frequency or larger and larger wavelengths. So that means we are saying that the fixed point has a property that the large wavelengths are defined by the theory with u star regardless of where you start. Okay, whether you start here or here, after many iterations you're going to hit there, assuming you're on the trajectory that goes to fixed point. So your long wavelength theory will be defined by that u star rather than u. So this is the aspect called universality, where you're saying the details of your original Hamiltonian which had a parameter u is not very important. Low energy phenomena, long wavelength, which is relevant for critical phenomena, is governed by the same u star regardless of what your u was. Okay. And u star has this value. So in some sense you know what the long distance behavior is even if you don't know your starting Hamiltonian parameters. So that's very nice. Okay, so let's make a few qualitative remarks. Yeah.
So where is the origin of this 4 in t minus 4? Somewhere they calculate.
Oh, this one.
Yeah.
So actually it's just,
Because you are halving the.
well, that halving fixes the 2.
Okay.
This is the dimension. It's actually the dimension of the lambda phi 4 coupling.
Okay.
So in 4 dimensions, when d equals 4, it's precisely dimensionless. When d is less than 4, it's a relevant thing, it gets bigger. When d is greater than 4, it gets smaller. So this is just precisely the dimension of the coupling. Yeah.
Okay.
So just like here, it was 2 squared.
Hence my question would be,
Yeah.
suppose you started with not sigma to the low but sigma to the 6 sigma.
Yes.
You get b minus 3.
Then you would get, yeah, then it would be, then in 4 dimensions, that would be a irrelevant variable. Yeah, it would get smaller and smaller and smaller.
You get the natural epsilon to be b minus 3. It's renormalizing exactly.
Oh yes, so yeah, if you start with sigma to the power of 6, d equals 3 will be the renormalizing point. So you should get a non-trivial theory at d equals 3. Whether it's stable or not, I don't know. Yeah.
Well, there are multiple theories.
Yes. Right. So if you had, so this is in phi 4 theory. So the point is that if you start with a higher, instead of phi 4, you start with a phi 6 theory, then instead of 4 minus d, you'll get something like 3 minus d here. Okay. And then this epsilon will be the deviation from 3, not 4. So so there are many theories you can study like that. Okay, so let's compare with the Gaussian case. So I'm going to say something qualitatively and then we'll do it a little more quantitatively in a few minutes. So first of all, in the Gaussian case, you had R naught equals 0, U naught equals 0. That was your starting point. Sorry, I shouldn't say R naught. Gaussian case U naught equals 0. So if R naught equals 0, then it remains 0. Okay. Gaussian case there is no U naught, it's just R naught, and we know that R naught, R1 is just 4 times R naught. So if R naught is 0, it remains 0. So that's your fixed point. What we call R star is just 0. And then we define this as the critical temperature. We said T equals Tc. So I said in critical phenomena, the parameter that you tune to make it critical is T equals Tc. Okay. Now we have a slightly more complicated situation because there are 2 parameters. So this is the Gaussian case. Now we have 2 parameters. Okay. So here T was just identified with R. So remember we said that R is basically to be identified with T minus Tc. Okay. Here what do we do? So well, you have one parameter T to tune and 2 couplings. So obviously you can't fix both of them. So this gives a relation. So tuning T gives a relation between UC and RC. So if you define a critical temperature and say I'm going to tune T to Tc, that will give me a relation between the critical U and the critical R, which will depend on the T. Okay, so you'll have something like this. So you'll have well, okay. So let me write it this way. So critical temperature RTC is some number we'll call RC, and UTC will be some number called UC. And as you tune T, there will be some relation between RC and UC. You expect that at this critical temperature, at this value T equals Tc, that means these values, your C goes to infinity. In some sense that defines for us critical behavior, and we'll define that as T equals Tc, C goes to infinity. But there is another way to define the critical temperature, which I will do in a minute, which will lead to the same conclusion, a more precise definition. Okay, so this is some value. So as far as your initial Hamiltonian is concerned, so you have R naught. So if you have 2 parameters to select, R naught and U naught, and the claim is that you can define a temperature dependence for these 2. So it's one parameter to govern 2, such that at T equals Tc, this theory flows, this theory is critical, which means C is infinity, and as you iterate, R goes to R star, U goes to U star. So I'm making now 2 statements here. That means there exists some critical temperature. So I'm giving you a set of 1 parameter family of couplings, R naught and U naught, as a function of T, and I'm saying that if you tune them to a particular value, which will be governed, which will define that temperature as T equals Tc. So this has some particular value for a given Tc. Then as you iterate, as you iterate the RG, this will flow towards a fixed point, and all along that trajectory C will be infinite. Okay. So so we'll show this in a minute in some detail, but I hope you understand what I'm saying. Let me draw a figure. So let me draw U and R. So this is let's say this is your fixed point. Okay. So there is some line here. So it's a relation between R and U, some curve, I've drawn it as a line here, such that if you start anywhere along this line, your R0 and U0 are anywhere along this line, then as you iterate, you will go towards this point. Okay. So this is your, let's say, R0 TC and U0 TC. If your T is not equal to TC, you're somewhere else, you're not on this line. So this is R0 T, U0 T, where T is not equal to TC. So what I've said graphically amounts to this. There is some parameter that you can tune which will give a relation between R0 and U0. So there's a fixed relation given that T, the value of R0 and U0, well, I shouldn't say that this doesn't define a value. T defines a relation between R0 and U0. So maybe I shouldn't write it like this. I should say R0 is a function of T and U0. Let's put it that way. So given T and a U0, there is an R0. Okay, so there is one parameter such that when T equals TC, you're on this curve. Okay, so you pick any U0, there's an R0. So this is your U0, there's an R0. Pick any U0, there's an R0. So as a function of U0 and T, there's an R0. So that at T equals TC, this is the curve. So this curve is called the critical surface. Okay. So okay, so let me just to reiterate. If I choose any R0 and T, there is a corresponding any U0 and T, there is a corresponding R0, such that when T equals TC, this R0 has a critical value, and you're lying. Critical value means you're lying on the surface, such that, and the surface has a property that when you iterate, you go along the surface and you hit the fixed point. This is your fixed point. Fixed point is that RC, R star, and U star. Okay, and we'll say that this defines a critical surface, and all values of T such that you lie on this critical surface are called the critical temperature. So that defines the critical temperature. Okay. So what happens if you are away from this critical surface? You can see, so typically what will happen is the deviation from this surface will be proportional to T minus TC. So we'll see this quantitatively in a minute. So you start off somewhere here. What will happen is initially you will approach this curve. You will approach this curve, but you won't hit the fixed point. Okay. What will happen is you will at some point you will deviate and you will go off like that. Okay. And the further you are from the curve, your initial point, the sooner you start deviating. Okay. So you can imagine starting from here you'll go like that. Imagine starting from here you'll go like that. Imagine starting very close to the curve. You'll almost hit this point, but then you'll start deviating. If you're right on this curve, you'll hit that point and stop. Okay. So actually this defines a very unique trajectory that you can imagine taking the limit as you approach this, but you're not quite at that. That limit, all these trajectories will asymptote to some curve like that. Okay. And this curve is a universal feature of your model. So in other words, all curves, all points that you start close to the critical surface will sort of asymptote to this, and if you're right at the critical or infinitesimally away, you will go on this curve. If you're exactly on the critical surface, you'll go to the fixed point. Okay. So there's a unique trajectory. This is often given a name. I think it's called the renormalized trajectory or something. Where do these things go? Well, you can see that R is always getting bigger. it's getting bigger by a factor of 4. Okay? So unless you are exactly at the critical surface, your R is going to go off to infinity. R infinity means your C is 0. Okay, so naively, unless there is something not trivial, what all these theories are going to go either to this fixed point where C is infinite, or to that fixed point where C is 0. Okay, when C is 0, there are no degrees of freedom in your theory. So in some sense, it's not very interesting. So if you go all the way there, you'll end up with a theory with nothing. So this is roughly speaking the simplest behavior you expect in a theory as you do the iteration. Okay, so to summarize, this surface is an interesting surface. It's called the critical surface, on which we'll see in a minute that C is infinite. Actually, the reason C is infinite is very intuitively very clear, because C is infinite at this point by construction. Why? Because at the fixed point, CL plus 1 equals half CL. This has to hold at the fixed point, but at the fixed point, the parameters are the same, right? The parameters of the Hampton are not changed. So CL plus 1 must equal CL. If you apply the formula to calculate C, you have to get the same answer. So the only way this can happen is if it's infinite. Okay, so it implies why is this true? Because you're using the same, inputting the same parameters to your form. So remember, C is given a Hamiltonian, you calculate C, there's an expression for C in terms of the parameters. So the parameters are the same at the fixed point. After one iteration, you'll get the same C. But on the other hand, it has to be half of the old C. So the only way this can happen is it's infinite. So this is the point where it is definitely infinite. And all these points flow to that under the RG. They're all physically equivalent to it, therefore. So everywhere on this, C is infinite. Okay, is this logic clear? Yeah, so do you understand why C is infinite here? C is infinite here because both these have to hold. This holds always. This holds at the fixed point, because you have the same formula relating C to the parameters, and the parameters are the same. So this has to hold at the fixed point. If you put this and this together, it means at the fixed point C must be infinite. So you call it C star. Okay, is infinite. So here it's infinite. But when you do an RG, you're not changing the physics. The correlation length is a physical quantity. So the theory defined by this parameter and this parameter, if they're on the same trajectory, have to have the same value of C. So this point in particular has the same value of C as that point. So all these points on the same trajectory have the same C equals infinite. Okay. So this critical surface, therefore, can be defined in two ways. It's a surface such that if you sit on it, you will go to the fixed point. It's also the surface on which C is infinite. Okay. So it's both are valid. So this is the qualitative behavior that you expect, and now we're going to analyze this model and do all that a little more mathematically. So are there any questions about the qualitative behavior? Okay.
You are defining U star and R star by those two equations.
Yes, yes.
You are basically saying this definition of DC is hidden there.
Definition of?
DC is hidden there, or how DC is coming from these two equations.
Well, TC, okay, TC is so T is a parameter which, if you specify T and specify U, we're setting okay, so we're saying let's choose a parameter T such that for every U there is some TC at which R lies on this surface. So it's like this. So for a given U, there is some T which specifies an R, where T will give you it's some measure of the correlation length, let's say, such that at T equals TC, this should be on the critical surface. The critical surface is this one. Yeah. No, that's not a question.
Can I say?
Yes.
So given the theory in terms of R naught and U naught,
Yeah.
so if you do RG, so you go in steps, it follows a trajectory.
Yeah.
Given that one-dimensional line, what is the parameter on that line is T.
No, the parameter that defines that line.
Right.
So
So you are
when T
basically
equals
given a U and U0 and RG,
Yes.
I will not be able to hit R star and U star all the time.
No, no, that's right. Yeah, so let me, okay, so since that's a good, so the point is,
But why did I not see from there? I mean, this seems like it's jump. Why should I not see from those two equations? I cannot hit R star and U star from any R0, U0.
no, but you see that, sorry, oh, from any U0.
Ah,
Well, you can see that because you can see that for, this is going to get bigger and bigger, right?
yeah.
This is
good.
good.
Structure
Yeah.
there will
Yes.
have to be maintained.
That's right, yeah.
That-
So this is normally, remember for the Gaussian case, this had to be exactly 0. And now we're saying there are two conditions that have to be satisfied. And so those two conditions will specify where you're going to go. If you want to hit a fixed point, you have to be precisely there's only one point which satisfies that. Now the question is, the rest of the points, how do they behave? And generically, a point here will not go into that because you can see that it's going to get bigger and bigger. You can see, in fact, if you analyze it, that RL plus 1 is getting bigger and bigger. So clearly, it's not going to go into a fixed point except for a very special value. So that special value depends on what your U is. Okay, so for a given U, there is a special, and so you have a one parameter set of curves if you want. So this defines a curve in the plane. Choosing t equals tc defines that way. So this is the curve t equals tc. This is the curve t greater than tc. This defines a curve. So for any t, for any u naught, there is some r naught. So that's this point. And then there's a trajectory. Once this point is fixed, the trajectory is fixed. But we are classifying the trajectories by a one parameter t. The t equals tc is this trajectory.
You said that correlation length is infinite
Along that trajectory, yes.
What is the difference when I am going along the line? What do you
The parameters of the Hamiltonian keep changing, like this.
but still it has diverging?
Correlation length is infinite, yeah. But there are other properties will not be the same. So
Not
the
true phase transition, second order phase transition.
no correlation is infinite, so it's a critical point. But there are many parameters. Not all quantities are defined by just the correlation length. Correlation length is one quantity, but if you calculate various correlation lengths, correlations, they will not all come out the same. So they'll depend on where you are on this trajectory. But what is true is that the long distance behavior of if your points are far apart, they will all be governed by this value. So the high energy behavior will be different. So different points along this trajectory will have different high energy behavior or short distance behavior, but the long distance behavior will be governed by that. So the Hamiltonian being equivalent yeah. So in this I should also say that in this Hamiltonian I've dropped many terms, the higher dimension. If you actually kept all those terms, then everything would come out the same. It's a completely reversible thing. So for instance, I dropped the use a sigma 6 term, right? So suppose I do this iteration and keep everything, do it exactly, then there would be no difference physically between all those points. But then you would be moving in an infinite dimensional space. You would have many parameters to keep track of. So I'm just jumping ahead because later on we'll talk about the exact RG, where you will keep track of everything. But this RG keeps track of only these two couplings, so you can only compare low energy phenomena. So the low energy phenomena will be the same for H and HL and HL plus 1. So I hope it's clear what this diagram qualitatively represents. Then we'll do this more exactly in a minute. So let me do that now. Let me see if there's anything else I have to say. So now I want to analyze the behavior of perturbation. So we're going to analyze what happens when you're away from the fixed. How does a point behave when it's near but not on the fixed point? So that's linearized perturbation theory. Sorry, linearized, maybe I should just say linearized recursion relations. So let's write down the thing again. So I have the recursion here. So let's define the deviation. Small deviation. So I'll write UL equals U star plus XL. So X is a small deviation from UL, and RL is R star plus YL. Okay? Where R star is this value. R star and U star are these values. So I want to get a recursion relation for YL and XL instead of UL and RL. Just algebra. Okay? So we'll write, I won't work it out, I'll just work out the equation. So you get R star, so let's do that one, plus YL plus 1. So this is RL plus 1 is 4 times R star plus YL plus 3C times U star plus XL by 1 plus R star plus YL. Right? So I've just substituted these things into the right hand side. And if you linearize now, so you get the equation for YL plus 1 in terms of YL. So if you put YL plus 1 and XL to 0, this equation is satisfied by definition. Okay? So we look at the terms linear in YL plus 1 on this side, linear in YL and XL on that side. That's what I mean by linearized recursion relation. Because this has, when you expand it, you'll get all powers of YL, but we just keep the linear term. So the linear term is easy, you can just get it YL plus 1. So you'll get this 4 times, well, this will give you a term 4 times YL. And then what will you get from here? So you'll get 3C, so then get 3C U star by 1 plus R star times XL. And then when you expand this YL, you will get some term which is, I think, minus what? 3, how much? 12C U star by 1 plus R star squared YL, something like that. Let me see, is this right? Ah, correct. We'll see. Ah, this is, sorry, this is not 3. This is 4 multiplying it, so this is 12. And it's a minus sign, I think. Plus sign. Why is it a plus sign? Wait. Oh. Which one am I doing now? R star XL. Oh no, this is a plus sign. Sorry, yeah. This is just 4 times 3C times U star times 4 times 3C times XL. That's all this is. Oh, there's no U star here. Yeah, there's no U star here. Right. So I'll just write it more neatly. We'll see. So this is actually 4 minus 12C U star by 1 plus R squared times YL plus 12C by 1 plus R star times XL. So this is YL plus 1. Okay. So I'll just write out what XL plus 1 is. So XL plus 1 is 2. So X defines U. Okay. So it's 2 to the power of epsilon 1 minus 18CU by 1 plus R squared. So this is understood to be star times X plus 2 to the power of epsilon 18CU squared by 1 plus R cubed times Y. So that's a recursion relation. So this is XL, YL. So that's what you get. So you just repeat these steps for the x recursion, you'll get that. So I won't work that out. So let's write it as a matrix. So let's write it as a matrix y l plus 1 x l plus 1 some matrix times y l x l, and this matrix is the following not very nice looking thing. Oh, I didn't work it out. I just like you did the YL, you repeat the steps for the XL, this equation. I've erased the equation. I had the recursion relation for U and R. I worked out explicitly the R. Same way you work out the U. Just take the linear part, you'll get this. Okay, now this matrix has two eigenvalues, and it turns out that the eigenvectors are different because it's not symmetric. The eigenvectors on the right are different from the eigenvectors on the left. So we'll use that. So I'll use this bracket notation to write, to define and M. So these are the two eigenvectors for the matrix. And when I say it's not the same on the eigenvector values are the same, the following is also true. And the following is also true. Vi, you can choose a normalization, this is true, but V is not the same as W. So I'll write it out explicitly. So W1 is 1, 0. So this is the basis where 1 corresponds to, which is 1. 1 corresponds to R, so we are writing it in the basis RU. Okay, so the top number corresponds to the R, bottom number corresponds to the U in that basis. W1 is that. So this is in the basis RU, and W2 is it's a complicated one. Minus 4C 1 plus 5 by 9 epsilon log 2 and 1. So you can check that if you act with this matrix on that, you will get two eigenvalues. When I will write down the eigenvalue, lambda 1.
Sorry, this vector is in small epsilon or exact epsilon?
Well, this is just,
Exact epsilon.
yeah, this, oh, that's what you're saying. I think it's small epsilon. Yeah, yeah. 4 minus 3, no, 4 minus 4 by 3 epsilon log 2. Yeah, so you've linearized it. So it's 1. You just keep that. So lambda 1 is this, and lambda 2 is 1 minus epsilon log 2. Notice that this is less than 1, this is greater than 1. When epsilon is 0, this is precisely 1, this is precisely 4. So you can immediately see what this is. This is basically telling you how the U coupling changes, because exactly when epsilon is 0, the U coupling doesn't change. UL plus 1 is the same as UL. So that's it doesn't grow, that means. Whereas this tells you that the R coupling typically grows by a factor of 4 each time with corrections. So those are the eigenvalues. But the interesting thing is that the V1 and V2 are not the same. So if I write V1, turns out to be 1 4C 1 plus 5 by 9 epsilon log 2, and V2 is 0 1. And you can check this. You can check that V1 with W1 is 1, which it is clearly, and V1 with W2 is 0 because of that minus sign. Okay. Similarly, V2 with W1 is 0, V2 with W2 is 1. So you can check this relation. So is this clear? This is just some algebra, you have to work it out. I'm just giving you the answers. So in this bracket notation, you can write down the matrix. So you can write the matrix M as lambda 1 okay. Well, I mean this is obvious, because if you act on, so M on if you act on this with W1, you put a W1 here, W1 with V2 is 0, so this doesn't contribute. W1 with V1 is 1, so you just get lambda 1 W1. Okay. Similarly, if you put a V1 on this side, this will give you lambda 1, V1 with W2 0, so this will go off. So you can easily check that M with W1 is lambda 1 W1, etc. Check. Okay. Okay, now our original basis, so our original basis of course is R and U, so we'll call that basis S. So I'll write it as some y times y plus x times x, where x represents what? X represents this guy, y represents this guy. So that's the basis 1 0 0 1. So M acting on because you will be given when you pick a Hamiltonian, you will be given things in this basis. Okay, so this will be your what do we call it, R minus R star, and this will be your U minus U star. I think X was for U, right? Yes. So this will be U minus U star, and this will be R minus R star. That's the information you'll be given. And you have to work with this matrix. So M acting on this is basically what? Lambda 1 on that plus lambda 2 okay. So we need this guy and this guy in this basis. Okay. So let's write V1S as, so what is our V1? This is our values. Okay. So I'll write this as V1 V11 times S1 plus V12 times S2. So by S1 and S2 I mean, okay, I mean Y and X. So I call this. So what is our V11? It's this. So I'll just give it names here. So this is your V11. This is your V12. Okay. And if I, the same way, if I write what S with W1, I can write this as S1 times W11 plus S2 times W22, where S1 is again the first S1 is we are working in the basis where this is R and U. So S1 is this quantity, R minus R star, and S2 is U minus U star. And W11 from here you can see W11 is this, W12 is 0. Okay, so W11 is basically 1, W12 is 0. Oh, sorry, this is W22. So this is W12. So what is W11? It's this one. W12 is that. W21 is this. W22 is that. And then V11 is this. V12 is that. V21 is this. V22 is that. So just change of basis. Okay. Why are we doing this? Because we want to know what happens when you iterate a given S, which is given X and Y. What happens when you iterate? So we'll take your S, put it in this W basis, act on it, and go back to this. So I'll just, I can erase this, I think. So we need to calculate M with S. So you have the nth iteration, you have some value of S. What do I mean by S? It means you have some xn and yn. Which order, or yn and xn. So this is the, I always get confused. Yn was the R, oh God. Y was the R. So this was the R minus R star, and this is U minus U star. So these are the values you're given, what we're calling the base is S, and you have to calculate yn plus 1 and xn plus 1. So you act on it like that, and this will give you M, and you write M as lambda 1 plus lambda 2 right. So what is this? So this, okay, so let's plug this in. So, and we want to get the n plus 1th. Okay, so yn plus 1 is so yn plus 1 is basically y with Sn plus 1, and xn plus 1 is basically x with Sn plus 1, and this is what we're calling Sn plus 1. Okay, so Sn plus 1 is m times that, is all that. And then yn plus 1 is obtained by taking the y projection with that, and xn plus 1 is the x projection with that. So we just have to work this out. So let's work it out. So let's work out yn plus 1. So yn plus 1, and then you can do x similarly. You put in a y here, so lambda 1 Okay, so what is this? This is final. Y with W1 is this 1, 1. And V with this one is, wait, where have I written down? So this is V11 times, where have I written it? V11 times, oh dear. So I have to do V1 with S. Did I do that?
Yeah. V1 on S1 plus V2.
This one. Okay. So that's V11 S1. So S1 is the first one, is Yn plus V12 Xn plus lambda 2 times W21 times this thing. So this is V21 Yn plus V22 Xn. So this is Yn plus 1. Okay? Just put the predictions. It should be clear what happens when you act with m squared. This lambda 1 becomes lambda 1 squared, lambda 2 will become lambda 2 squared. So all that happens is this gets squared, this gets squared, this gets squared, this gets squared when I act twice. So if I act on it with n times, in my notation it's L and L plus n. Okay, so it doesn't matter. So let's say you're doing it m times. I'll change notation. Then this will become m. That's all. Okay? Now, and similarly you can write something for, but before I do that, so now lambda, what is the value of lambda? Lambda 1 is much larger than lambda 2. Lambda 1 is growing, so when you do it m times, this is going to become a big number and this is essentially negligible. So we can drop these terms for a first approximation. Compared to lambda 1, because this is starting off as 4 to the power of m. So it's going to be huge, exponentially large compared to that. So we can neglect this. Okay. So your conclusion is, let's write out this. Now again I forget y is r. So let's write out. Now I've used my notation L and n instead of m. So r L plus n. So this is what it is, except I've chosen this to be L and this to be n. Sorry for the confusion, but I should have followed my notes more closely. So remember, this is a deviation from r star. So our deviation from r star is lambda 1 to the power of n W11 V1 times r L minus r star plus V12 UL minus U star. Is this clear? So I've called it, maybe I'll just change it here itself. So let's call this L, let's call this N. Okay. These are the deviations. And when you do it m times, all that happens is becomes lambda 1 to the power of n. And I've neglected the lambda 2 compared to this because it's a small number. And this is the equation for r. If you go through the same steps, you'll get an equation for u is lambda 1 to the power of n times W12 times V11 RL minus R star plus V12 times UL minus U star. So the only difference is it's W11 and W12. The rest of it is the same because I've neglected the lambda 2 eigenvalue. So this defines the behavior near the fixed point. Okay. So is this clear so far? With respect to lambda 1. See, when you do lambda 2 to the power of n, it's approximately 1. This becomes 4 to the power of n. So if you imagine n is 20, you're comparing 4 to the power of 20 with 1. So it's completely negligible. So I will erase all these. Yeah. Yeah, it's actually less than 1, marginally. Okay, so let's just let me now the comments that I made when I drew that diagram I'll just repeat with this equation demonstrate. So first of all, remember in the Gaussian case we had no u, all we had was r. Okay, so in the Gaussian case, so I'm just repeating r. In the Gaussian case, t equals Tc implies that r equals r star equals 0. That we know by now. Critical temperature means r equals rc, which is 0. Now here, if you choose t equals Tc, you can't fix 2 parameters, you tune 1 parameter, so you can't hope to fix both u and r, but you can get a relation between them. Okay, so a relation between u and r. Okay, so for any, let me put it this, for any u naught, there will be a critical r naught c such that t equals Tc. So if you start with u naught, choosing t equals Tc is equivalent to fixing that r naught c. In other words, r naught c is a function of the u naught that you start with. Okay? This is a critical value, that means you tune t equals Tc. For any u naught, there is some r naught c. So that is this curve. For any u naught, there is some r naught c at which t equals Tc. Okay. And okay, so now iterate. So you choose that value and iterate the Rg. Okay. What you expect is that RL will go to R star and UL will go to U star. That's the definition of being at the critical point. Okay, and we will see what this implies in terms of this in a minute. Okay.
This R naught C can be on either side of the fixed point or only one side?
What do you mean side?
You have drawn this asymptotic line, right? So this line ends at that fixed point.
This one. This is a fixed point.
That ends there.
Yeah.
You also drawn the asymptotic curve.
This one. Yes.
Can that R naught C be on either side of the fixed point on this extended line or not? Or will it always be on this segment?
That's the end point.
You mean could the line have been like this?
So for U naught there is an R naught C.
Are you saying there could have been a curve like that? That's no.
So you have this line which ends at the fixed point.
Yes.
You also extended it.
This is some trajectory.
Right. With
As a-
normalized time.
yes. Yes.
That critical line is not extended.
This is not a critical line.
They
So
are
maybe
those lines which
this
are
is the
close
critical
to
line.
critical line.
Critical line is all the points that go and end there. That's all. Yeah.
R naught C will always
Yeah.
be on
Yeah. So if you iterate at t equals Tc. So if you're at the t equals Tc, the iteration will take you to that critical point. If you're not at t equals Tc, it will not. That defines, so this defines your Tc by definition. I'm defining it that as my Tc. Okay, if t is not, so let me write it to be very precise, it will not go to the fixed point. Okay, so I mean that's just a definition of TC as the set of points that go to the fixed line, fixed point.
Are not found in an epsilon expansion.
The critical, the fixed point, yeah.
Right.
Yes.
The first order.
Yes.
So is that epsilon expansion an asymptotic expansion or is it?
I think it's an asymptotic expansion. Yeah. It's. I mean, yeah. I don't know. I don't actually. I think existence is probably not in question. In the sense that. Yeah, but that just means that the perturbation that series breaks down, but that doesn't mean that the fixed point doesn't exist. So okay, I actually don't know the full status, but I believe that for d less than 4, there is a fixed point. Whether the series converges to that, I'm not sure. Yeah. Actually, I have to check that, but I think that's true. Yeah. Okay, so as I said, if t is not equal to series, it will not go to the fixed point. Suppose we have a theory with tunable parameter t. So we'll write. So we have r naught of t and u naught of t. So just imagine we have a Hamiltonian, and the parameters r naught and u naught depend on some parameter called the t, which you identify as the temperature. And by our definition, r naught of Tc equals r naught c, and u naught of Tc equals u naught c. Okay, that was our definition of Tc. So now we study T not exactly equal to Tc, but T near, but near. Sorry? Am I studying what?
Different analysis or is it nested?
Oh, is it time to stop? Ah, okay, good point. Yeah, so it's a continuation, but I'll do it next time then. No, it'll take some time. So okay, thanks for reminding me. So we'll stop here. But if there are any questions, please. So what I want to show is that there exists some condition on this for this behavior to be true, and I want to show that the critical C has a certain, there's a certain divergence behavior for the critical, I mean the correlation length as t approaches Tc, etc., as follows from this analysis. So we'll do that next time. Yes. Yes.
So now, going towards the fixed point,
Yes.
will it be dictated by some physical parameters or this iterative process?
Iterative process. So you're getting a series of approximations to your original Hamiltonian, which has a property that the parameters go to the fixed point, independent of what you started with. And this Hamiltonian is good for low energy phenomena, this fixed point Hamiltonian, regardless of what your original Hamiltonian was. So the statement, okay, so to summarize, whatever h naught you start with, as long as it's in the region of this fixed point, I mean as going towards is controlled by this fixed point, the low energy behavior will be governed, low energy behavior of your correlation functions will be governed by this value, regardless of what you start with. That's the bottom line. Okay? This Hamiltonian has the property that it goes to that fixed point, but the low energy behavior will be governed precisely by u star and r star. So you don't need to know the value of u naught and r naught. You can work with this Hamiltonian, critical Hamiltonian. Okay? And then there's some issues about what happens if you're not exactly at the critical point and at some point it will diverge. So there's some region in which you can use this Hamiltonian, the region of validity. Okay, you cannot, unless you're exactly at the critical. So you basically you should stop your iterations when you reach the correlation length. That's our starting assumption anyway. If the correlation length is infinite, you can keep going. You'll hit the fixed point. If it's finite, you should stop when you reach the correlation length. Otherwise, you won't get anything useful. After that, beyond that, if you keep iterating, you just go off. You won't get anything useful.
There's already notion of anomalous dimensions.
Yes, this the fact that lambda is not 1 is the fact that it's not given by dimension. So this lambda 1, yeah, it's not 1 and 4 is an anomalous dimension.
Expansion in epsilon is not really tied to some loop expansion so far.
No, it's not a loop expansion because this all came at one loop. It's not a loop expansion. It's some. It's a bit like what happens in many of these two-dimensional models, where this expansion would.
This is kind of dimensional regularization.
Yeah, if you do string theory or two-dimensional models, then the analog of this epsilon is basically the dimension of your operator, which comes from the normal ordering, gives you the normal dimension, and fixes the basic it's sum to all loops. So, but if you study a very specific model, in 2 dimensions, it's very easy to see all this. Okay, so we'll stop.
So for this 5-4 model, if you put epsilon equals 1,